Hello everybody, welcome back to my channel where we solve rather difficult integrals. And today's integrals are two definite integrals from 0 to 1. First, of the square root of 1 minus x by 1 plus x. The second one, the square root of 1 minus x squared by 1 plus x squared. The first integral is not very difficult to evaluate, but the way we solve it may help us figure out how we can evaluate our second integral, which is obviously much more complicated than the first one. When we try to solve the first integral, the first reflex I had is to let 1 minus x by 1 plus x being a new variable with a u substitution. It's called the Weierstrass substitution. It is very useful when you have 1 minus x by 1 plus x because the substitution reverses itself. If you say 1 minus x by 1 plus x equals, for example, phi, then 1 minus phi by 1 plus phi equals, indeed, x. And the segment 0 to 1 is reversed to itself. Here, 0 goes to 1, and 1 goes to 0. So it is a very useful substitution, but it is very, very specific. And if, for example, we had other boundaries like negative 1/2 and 1/2, we will not be able to do this substitution because, well, once we did this substitution, we get square root of phi divided by 1 plus phi squared, which is not very useful to integrate if you don't have the perfect boundaries. So it works in this case, but it is not very useful in general if you want to evaluate other integrals, and even worse, in this case it won't work, because if you do, for example, 1 minus x squared by 1 plus x squared equals phi, then you will have square root of phi after the substitution, and because of the dx you will have something like 1 by phi to the 4th power, which is impossible to integrate with the square root. So this substitution is useful in this case, but won't help us evaluate j. So we may think about something else. Usually in this kind of cases, a trigonometric substitution may help us, because if you let x being equal, for example, to cosine of 2 theta, then 1 minus x is somehow easy to write, and 1 plus x is as well easy to write. And even with the square root, it is very useful. Here 1 minus x and 1 plus x are something to the 2nd power, because here cosine 2 theta equals, firstly, 1 minus 2 cosine squared theta, and also 2 sine squared theta minus 1. So you see that here, if you subtract 1, it is something squared, and if you add 1, it is something else squared. So very, very useful substitution, and it is in my opinion, better method to solve this integral than the Weierstrass substitution, because it is not dependent on the boundaries. Here, even if we had negative 1/2 and 1/2, it would be very easy to give the result of this integral. So better method, but again, it won't work here because we have x squared. You see that if we want to apply this substitution to our second integral j, we need to let x squared being equal to cosine 2 theta. But then we miss some x here in front of the dx, because when you differentiate here, the differential elements, we have 2x dx equals negative 2 sine 2 theta d theta. And even though the square root here is easy to write, in the end you have to here divide by x to isolate our dx, and you have sine 2 theta divided by square root of cosine 2 theta, which is very, very difficult to integrate. So this substitution is a very solid one in this case, but not in this one, because with the x squared it is almost impossible to integrate our dx here. So we have to think about some other way to integrate this, and the way we will do it is, as usual, special functions. In here we know that we have the boundaries being 0 and 1, and this is a very good news, because we have plenty of special functions which are defined as definite integrals from 0 to 1. In here we may be tempted to get the beta function involved. So just to refresh your memory, the beta function is defined for two arguments, beta of a, b, equals the integral from 0 to 1 of x to the a minus 1 times 1 minus x to the b minus 1 dx. Here we have square root of 1 minus x, which is perfect because here we have 1 minus x to the anything power, so very good news. And here we have 1 plus x under square root, which is a very bad news, because here we have x, 1 minus x, but not 1 plus x. The good news is we can get rid totally of this 1 plus x by a little trick. In this kind of integrals, the powers of x are not very important. You can always do a substitution, like x to the t goes to x, with x being a new variable of integration, because here you see that we have 0 to 1, so this substitution won't change the boundaries, and in here you see that if you change the power of x, then it will only change the value of our argument, but we are still able to use the beta function. So in here we need to get rid of our 1 plus x under square root with a trick, and here we go. I equals the integral from 0 to 1 of 1 minus x under square root divided by 1 plus x under square root, and we will multiply both sides by square root of 1 minus x. No, not plus. 1 minus x again. Other way, we will change the result, and we don't want this. So here we have exactly the same integral, but in here you have 1 plus x times 1 minus x, and all that under square root. And here we have 1 minus x under square root, which gives us 1 minus x. So here our integral is nothing but the integral from 0 to 1 of 1 minus x, all divided by square root 1 minus x squared dx. And maybe you see it now. We can just do a substitution, x squared goes to x, and then we will get two values of the beta function. Here we have 1 by square root 1 minus x, well, x squared, but after the substitution you get the idea. And here you have x by square root 1 minus x squared, and both functions can be integrated from 0 to 1, obviously, thanks to the beta function. So our first integral is from 0 to 1 of, well, dx by square root 1 minus x squared. And the second one, from 0 to 1, x dx by square root 1 minus x squared. And then we let x squared in both cases being equal to, let's say, t. Then 2x dx equals dt, and dx equals dt by 2 square root t. So in here our integral I is nothing but the integral from where to where. Well, obviously this substitution doesn't change our boundaries. So we have 0 to 1 again. Dx is nothing but dt by 2 square root t. And we have here square root 1 minus t. So I can put a 1/2 in here. We have dx, which is so 1 by square root t. So let's say t to the negative 1/2 power. And here 1 minus t to the negative 1/2 power. And this can be calculated using the beta function. And our second integral, we have x, which is square root t, and then we have easier, we have here x dx being equal to dt by 2. So we just have minus 1 by square root 1 minus t, and then we have a dt, and 1 by square root 1 minus t is nothing but 1 minus t to the negative 1/2, the same power as here. So I equals 1/2 of beta. Here we mustn't miss this negative 1 here, so here the argument is positive 1/2, and here the argument is again positive 1/2. And then we subtract beta of, here we don't have t to the anything power, which means we have t to the 0th power, so a minus 1 equals 0, and then a equals 1, so 1/2. Alright, and we know the identity, beta of ab equals gamma a, gamma b divided by gamma a plus b. So in here you have I being equal to 1/2 of beta 1, which is gamma 1/2 by gamma 1. We know that, well, we need two identities to define the gamma function. Gamma z plus 1 equals z gamma z, and gamma 1 equals 1, and well, a third one, gamma 1/2 equals square root of pi. So in here you have square root pi 1. So we have a pi divided by 1, and then we subtract beta 1/2, which is gamma 1, gamma 1/2, gamma 3/2. So we have 1 square root pi, and then we have gamma 3/2, and using this identity it is equal to 1/2 times square root pi. Here divided by 2. Alright, and then square root pi's cancel out, and here we have pi minus 1/2 all divided by 2. Now here we have pi minus 1 by 1/2, so pi minus 2. So the result of our integral is nothing but pi minus 2 all divided by 2. Alright, now we are able to solve our second integral, j being equal to the integral from 0 to 1 of square root 1 minus x² by 1 plus x² dx. And we will do the same trick. So here j of, well, that's it, equals the integral from 0 to 1, 1 minus x², 1 plus x², and then we multiply both sides by square root 1 plus x². No, 1 minus x² again. I tricked myself. 1 minus x² here, 1 minus x², we get 1 square root, 2 square roots, and dx, which is the integral from 0 to 1 of, here we have 1 minus x squared, 1 minus x squared, so the square roots cancel out, and in the denominator we get 1 plus x squared times 1 minus x squared under square root, which is square root 1 minus x to the fourth power. So we have 1 minus x squared divided by square root 1 minus x fourth. The x and, well, centric, we split the integral. This can be calculated, and this can also be calculated. So here we have, well, first we do the substitution, x to the fourth power being equal to t, x equals t to the 1/4. The x equals 1/4, t to the negative 3/2 dt. Is it? Yep. So j is nothing but the integral from 0 to 1 of, well, in this case we have only 1 and then the x, so we can just put a 1/4 in front of everything, and then we have t to the negative 3/4. All divided by square root 1 minus t. Then we subtract x squared, which is square root t, times t to the negative 3/4, which is t to the negative 1/4, all divided by square root 1 minus t dt. So again, this is nothing but 1 minus t to the negative 1/2 power. So we have 1/4 times beta of first argument being 1/4, because we don't forget the -1 here in the argument. And here we have negative 1/2, which is for the beta argument 1/2. So we have here beta 1/4 1/2 minus beta 3/4 1/2. And when we try to evaluate this, pretty easy, j equals 1/4 of beta 1/4 1/2 is, again, we use this identity, so we have gamma 1/4 gamma 1/2 by gamma 3/4 minus gamma 3/4 times gamma 1/2 by gamma 5/4. And, well, we know that gamma 1/4 cannot be expressed in terms of usual constant, like, I don't know, square root pi or anything. So we have to keep gamma 1/4 as itself, but gamma 3/4 can be expressed in terms of gamma 1/4. How do we do this? We use the reflection formula for the gamma function, which is the well-known gamma theta gamma 1 minus theta equals pi cosecant pi theta, which proves that here you can let theta be equal to 1/4, gamma 1/4, gamma 3/4 equals pi cosecant of pi by 4, which is square root 2. So here we have pi square root 2. Here we have gamma 5 by 4, which is nothing but 1/4 times gamma 1/4. Here we have gamma 3/4 being equal to pi square root 2 by gamma 1/4. So j equals 1/4 times gamma 1/4 square root pi, all divided by pi square root 2 divided by gamma 1/4, which is pi square root 2, and in here we put gamma squared of 1/4. Here we have the opposite thing. We have gamma 3/4, which is pi square root 2. Here we have gamma 1/2, which is square root pi, and here we get 1/4 of gamma 1/4. But remember, here we had gamma 3/4, which is so we have to add an extra gamma 1/4. So here we put a squared, and then we can just write again our integral j, 1 big fraction. In here you have gamma squared. I will just let gamma be a constant equal to gamma 1/4. So we have gamma squared, here square root pi and pi, so gamma squared by 4 square root pi square root 2 minus pi square root pi square root 2 divided by, and here we have 1/4 and 1 by 1/4, so cancel out, and we have here gamma squared. So in terms of one fraction, we have, let's say for the denominator we get 8 gamma squared square root pi, and the denominator we have here we have the gamma squared, we have an extra gamma squared, so gamma 4th times square root 2, because here we multiplied by square root 2 in the denominator, and we subtract, and here you have pi to the 3/2 power, and we just added square root pi, so we have pi squared, and we have to multiply by we multiplied here by 8, so we have 8 square root 2. Alright, and I think I didn't do any mistake here. No mistake here. So we just proved that the integral from 0 to 1 of 1 minus x squared by 1 plus x squared dx equals gamma 4th of 1/4, well, gamma to the 4th power of 1/4 minus 8 pi squared, all divided by let's say 4 gamma squared of 1/4 times square root 2 pi. Well, I hope you enjoyed the video. This integral was a pretty tough one. Well, not so much, maybe not as usual. Well, see you next time for the next integral. I don't know yet which integral we will calculate, but until then, study, learn, and progress. See you next time.